Evet, sınıfın yarısını kaybettirmeyi başarmışım. Yani. İyi bile bence. Yani bu konuda şey olmuş. Ama az kaldı. Yani bu haftayı atlatırsanız acının çok büyük kısmı bitiyor yani. Ondan sonra stage space. Stage space kısmı yani çok discourage etmek istemiyorum ama derse gelmesem bile ben yaparım yani. Ama buralarda şey önemli. Birazcık ne olup bittiğini görseniz bile. Yani hepsini anlatamayabiliyorum yani. Şey yapamayabiliyorum. Yani geçiremeyebilirim yani tam olarak açık fikrini. Çünkü kendiniz yapmadan bazı şeyler öğrenilmiyor kolay kolay. Onları geçiremeyebilirim ama yani ne olup bittiğini birazcık sadece temel fikirleri geçirebilsem benim için kârdır diye düşünüyorum. Okay, we have found we have completed step 4, which is the uncompensated system has the phase margin equal to 17 degrees. Okay, so now we are going to go into step 5. Find the phase increment phi max and to be added by the compensator and alpha. Okay. So here, what do we mean by the phase increment? So we know that we are going to actually add this phase somewhere around here, so that the phase margin increases to the required value. Okay? But as I told you, here, if this magnitude was equal to 0 dB all the time, if this magnitude was 1 all the time, which is 0 dB, then I could have added this magnitude, added this phase without any side effects. Okay? In that case, I would have chosen my phase increment phi max 45 minus 17. Okay? But here I cannot do that, because when I try to add that phase somewhere around here, then the magnitude curve, there is a positive magnitude there. And that magnitude shifts this magnitude curve to the right a little bit. Okay? When that magnitude is shifted above, this gain crossover frequency shifts to the right. Okay? But that reduces even more the phase of the system. That means that the actual phase margin will not be equal to 17, but it's going to be even lower. Assuming that decrease is negligible, it is between 0 and 5 degrees, I can still do something. I can actually give this make this phi max a little bit larger than the actual required value. By adding an error margin, I can try to get rid of that problem. Okay? So we choose this phi max as follows. So phi max is equal to, I write phase margin required, that is the required phase margin, which is 45. Okay? And minus phase margin uncompensated, okay? That is the value that we have found, it is 17, plus some error margin here. Okay? So I will add here 5 degree error margin. This is usually between 5 and 10, something like this, depending on the phase of the system. If phase is decreasing quite sharply, then I might add a larger error margin. Okay? But here 5 degree might be sufficient. So I would suggest you just add 5 degree initially. Okay? If things do not work, you might try to add a slightly larger error margin. Yes. Yes, but what is going to happen is that you are again going to be forcing the system. You are enforcing stricter requirements in that case. Okay, so generally we here again try to stay at the limits, at the boundaries. Okay, that is why we generally add the minimum that we can get away with. Okay. So here that is equal to, so this is 45 minus I have 17 and I have plus 5 degree. Okay? So this is going to be what? 33 degrees? It is something like this. I have found what phi max should be in my example. And I know that alpha is given by this formula. When I know phi max, I know what alpha has to be. Okay? So that is one of the design parameters. Alpha is going to be 1 minus sine 33 degrees divided by 1 plus sine 33 degrees. Okay? And in this case, if you calculate that, you are going to get the value given like this. This is 1 minus 0.54 divided by 1 plus 0.54. That is approximately 0.3. Okay? This is the alpha value that we get. So now the only remaining thing is to find our capital T value in our design. Okay? The only thing that is remaining is to find capital T. And that is going to be step 6. Place the peak phase phi max at the new gain crossover frequency. I will call this frequency as omega GC, compensated gain crossover frequency, and find T. So now we know what alpha is. Okay? Alpha has already been calculated here. Okay? And if I know alpha, I know how much magnitude is going to be added into this system. Okay? I know how much magnitude is going to be added to this system at the peak frequency. Okay? What I have to do is to make this frequency, I need to place this peak frequency at the new gain crossover frequency of the system. Okay? When I add this magnitude to this magnitude here, the gain crossover frequency of the system is going to shift. Okay? When it shifts, I'm going to obtain a new gain crossover frequency where this magnitude curve crosses 0 dB line. Okay? And then what I have to make sure here is that peak frequency, this omega m, which is this thing. This thing should be exactly at the new gain crossover frequency. So I want omega m, I want this frequency to be exactly the new gain crossover frequency. So now let us try to look at what has to happen here. So at the new gain crossover frequency, what is our condition? Our condition is going to be G uncompensated of J omega G times GC of J omega G, the magnitude multiplication of these two quantities at the new gain crossover frequency. They should be what? 1. The result should be 1. Okay? So at the new gain crossover frequency, this magnitude at the new gain crossover frequency, this magnitude and this magnitude, compensator magnitude, should be, their multiplication should be 1. Okay? So what I want to do is that I want to make the new gain crossover frequencies, I want to make it to be the peak frequency, peak phase frequency. Okay? I want this to be omega m. Okay? I want this gain crossover frequency to be the peak frequency, peak phase frequency, so that I benefit from the phase curve as much as possible. Okay? So then omega GC is omega m. What is this magnitude for the compensator at that peak frequency? It is 1 over what? This magnitude, GC of omega m magnitude, what is it? That magnitude there. 1?
1 over 1?
What do you mean? 1 over 1?
Just 1.
No, it's not 1. So I'm asking, at omega m, what is the magnitude of the compensator? Tell me in terms of alpha. That is in dB scale. In linear scale, what is it? In linear scale, what is the magnitude of GC of j omega m? 1 over square root alpha. So I know that this thing is 1 over square root of alpha there. Okay? Then what does this mean for G uncompensated j omega GC? This should be what in terms of alpha? According to that equation. It should be what? Siz benim istediğim türden bir şey söyleyin. Ne olması lazım? Yes, that is square root of alpha. Okay. Burası oldu mu? Burayı anlatamamış olabilirim yani ben. Büyük ihtimalle anlatamadım.
Hocam bir daha üzerinden geçsek olur.
Şimdi burada İngilizce ihtiyacı olan var mı? Burada önce bir Türkçe geçeceğim, ondan sonra bir daha İngilizce geçeceğim. 3 kere olacak yani, tamam mı? Şimdi, bu fazdan olabildiğince çok yararlanmaya çalışıyoruz. Yani gidip ben yeni gain crossover frekansla gidip şurada eklersem hiçbir işe yaramaz yani bu. Tamam, burada zaten azıcık faz var. Bu maksimum fazı yeni gain crossover frekansına yerleştirmeye çalışıyorum ki sistemin faz marjinini en çok artırabileyim. Tamam? Şimdi dolayısıyla şunu yapmak istiyorum. Buradaki peak fazın yaşandığı frekansı şeye koymak istiyorum. Yeni gain crossover frekansına koymak istiyorum. Yani yapmak istediğim şey aslında şu frekans 1 bölü kök alfa t'yi omega GC'ye eşitleyebilmek. Yeni gain crossover frekansına eşitleyebilmek. Tamam mı? Şimdi yeni gain crossover frekansında ne olması lazım? Yeni gain crossover frekansında open loop'un gain'i 1 olması lazım veya 0 dB olması lazım. Yeni gain, ya open loop sistemde şu. K ile G'yi birleştirdik, G uncompensated bulduk. Ve de GC bunlar open loop'un terimleri zaten. Open loop transfer fonksiyonunun terimleri. Bu gain'in yeni gain crossover frekansında 1'e eşit olması gerekiyor. Tamam mı? Ve de benim yapmaya çalıştığım şey omega GC'yi de omega M'e eşitlemek. Yani şu peak frekansın yeni gain crossover frekansında yaşanmasını istiyorum. Şimdi yeni gain crossover frekansı bu frekanssa buradaki magnitude'a bakıyorum. Buradaki magnitude yani GC of j omega'nın magnitude'u 1 bölü kök alfa. Tamam mı? Şu 1 bölü kök alfa. Bunların çarpımını benim 1 yapmam gerekiyordu. Tamam mı? Yani o zaman şunun kök alfa eşit olması lazım ki yeni gain crossover frekansında benim gain crossover frekans koşulum sağlansın. Hı -hı.
Burada gain crossover sağ kaydığı için ben 5 derece marjin ekliyoruz dedim ama 5 derece marjinin tamamen öylesine ekliyoruz gibi bir durum ortaya çıkıyor.
Neden? Şimdi şöyle, bunu ben yaparsam sistemin işte şu kök alfa yerine 0.3 koyacağım. Tamam mı? Şurada şunu hesapladığım zaman sistemin gain'inin şuralarda bir yere eşit olduğu frekansı bulacağım. Tamam mı? Şimdi bu frekansa baktığım zaman ben bu frekanstaki faza bakarsam 17 dereceden daha az faz marjım var. Tamam mı? O yüzden 5 dereceyi ekledim. Bu yeni frekans şu sağda bir yer olacak. Sistemin yeni gain crossover frekansı şu sağda bir yer olacak. Ve de buraya baktığımda eksi 163'ten daha az bir faz olduğu için faz marjin azalmış olacak 17 dereceden. Ve de o eklediğim 5 derece işte bunu telafi etmeye çalışıyor. Tamam mı? So here we want the new gain crossover frequency to be exactly this frequency, okay? And for this frequency to be the new gain crossover frequency, the magnitude of the open loop system should be 1 or 0 dB at the new gain crossover frequency. When I satisfy this equality, this new magnitude, the magnitude of the compensator is 1 over square root alpha. If I want to make the multiplication to be equal to 1, then the magnitude of the uncompensated system at the new gain crossover frequency should be square root alpha. Okay, so I can first find the new gain crossover frequency by using this equation, and then by equating this new gain crossover frequency to 1 over square root alpha t, I can find what t is. Okay, that is what we are doing here. So now here let us try to do this. So what I'm going to do is the following. So I will G uncompensated of j omega gc has to be square root of, I have found what alpha is, square root of 0.3. Okay? I have to solve this equation. So I know that G uncompensated of j omega is this thing. Okay? Let me write this magnitude once more. Okay? This is 10. Okay? And I have omega. The magnitude of that term is 1 plus omega square root. Okay? So this is equal to, I have 0.3 square root here. Okay? So now let me try to take the square of both sides. 100 divided by omega square, 1 plus omega square is equal to 0.3. Okay? And now if I write this equation, I'm going to get omega square, 1 plus omega square is equal to 100 divided by 0.3. This is approximately 333. Okay? So now I have to find the root of this equation once more. Okay? But here I know something. In the earlier case, the gain crossover frequency was somewhere here. It was approximately 3. Okay? And then, by neglecting this 1, I could obtain square root 10. Okay? So in the earlier case, we had the following equation. Omega square plus 1 plus omega square is equal to 100. This was the equation earlier. Okay? Because omega is approximately around 3, I have neglected this 1 because this thing is going to be around 10. Okay? So I neglected this thing, and then I could find omega square is equal to 10, and then omega was square root 10 approximately. Here omega is going to be even larger. Okay? Why is that? Because new gain crossover frequency is going to be somewhere here. Okay? It's going to be somewhere here. That means that this 1 is going to be even more negligible. Okay? So this thing is 0. That actually means that omega to the 4, omega gc to the 4 is approximately 333, and that means that omega gc is 4th root of 333. Okay? So this is approximately 4.3 radians per second. After finding this, what am I going to do?
Check the phase margin.
I can check the phase margin to verify what I did. But still the design is not complete. I will find T. How am I going to find capital T? Yes, we know the formula for omega m. Okay, I need to equate this omega gc to omega m, to this value. Okay, I know alpha. I know the result 4.3, then I need to extract what capital T is. So now what I'm going to do is that omega m, which is 1 over square root alpha times t, is equal to omega gc. It is 4.3 radians per second. Okay? And I know that in this case 1 over square root alpha is 0.3, t is equal to 4.3, meaning that t is 1 over 4.3 square root 0.3. Okay? And in this case, t is going to turn out to be 0.43 approximately. In this case, you can again, as your friend said, you can actually check whether your design has worked or not. How can you do that? You knew the new gain crossover frequency, 4.3. You can calculate the phase of the system at 4.3, and you can calculate how much phase is going to come from the system. If it is larger than what? If it is larger than something, you're going to be safe. The phase here was minus 163. Okay? If the new phase is larger than what, are you going to be safe? İngilizcem burada çok yetmiyor. Yani neyden yüksek olursa iyi durumdasınız demek oluyor. Eksi 163'ten, eksi 163 de öncesi. 4.3'te tekrar faz marjını hesaplarsanız ve o neden yüksek olursa bu iş çalışmış demektir. Eksi 168'den yüksek olursa. Neden? Çünkü 5 derece faz ekledik ya. Error margin ekledik orada. O 5 derecenin içinde kalmanız lazım. O 5 derecenin içinde kalmadıysanız bu işi daha yüksek bir error marginle yapmanız gerekir. Dönem sonunda iyice boşladı hocamız. İngilizce hak getire. Okay, it is not easy, but once you try to do it yourself, actually, you're going to learn it better. So the remaining procedure that I'm going to do here is not included in the design. But if you use this t value, then 1 over t is going to turn out to be 2.3 radians per second. Okay, and 1 over alpha t is going to turn out to be 7.7 radians per second. Okay? So here, that actually means that my corner frequency for the new system is going to be somewhere here, and the other corner frequency is going to be here. And here, around at value 4, is going to be my new gain crossover frequency. Okay? So here, when I look at what happens in the magnitude, when I add that compensator here is what is going to happen. The magnitude of the compensated system is going to continue to be the same until we hit the corner frequency, the first corner frequency, because this magnitude is 0 here in this interval. But afterward it's going to be positive, meaning that this magnitude is going to start increasing at that point, and it's going to pass from the new gain crossover frequency here. Okay? But it's going to continue increasing or deviating from the actual magnitude until we hit this corner frequency. Okay? And when we hit that corner frequency, it's going to continue becoming parallel afterwards. Okay? So this is my new magnitude, compensated magnitude of the system. Okay? And when you look at the compensated phase, you're actually going to get something like this. Around here, we're going to get the increase, and we will get the required phase margin like that. Any questions? Hiç şey yapmadım. Yani herhangi yeni bir calculation yapmadım. T'yi bulmuştum. Bir de alfayı da bulmuştum. Bunları hesapladım sadece. O değerlerle ne olması gerektiği. Ondan sonra onları burada yerine... Bunu genelde çizmemize gerek yok. Burada sadece bu ne oldu en sonunda onu göstermeye çalıştım. Corner frekansları buradaysa, corner frekansına, birinci corner frekansına gelinceye kadar compensated sistemin magnitude'da hiçbir değişme olmayacak. Çünkü sıfır kompansatörün magnitude. Ama ondan sonra bunlar farklılaşmaya başlayacak. Çünkü burada pozitif gain ekliyorum artık. Tamam mı? Bu pozitif gain'i nereye kadar ekliyorum? Ta şu ikinci corner frekansına kadar eklemem gerekiyor. Ortada bir yerde, yani tam ortada o frekansların şey var elimizde. İşte 4.3 radians per second'da new gain crossover frekansı var. Dolayısıyla bu frekansta sıfırdan geçmek durumundayım. Tamam mı? Yeni sistemin, compensated sistemin magnitude response'u burada sıfırdan geçiyor. 0 dB'den. Ama ondan sonra diğer corner frekansına kadar deviate etmeye devam edecek tabii ki. Yani çünkü şurada şu daha deviation devam ediyor burada pozitif magnitude. Ondan sonra geri kalanında da paralel olması lazım bu şey. Çünkü şu difference'ın sabit kaldığını biliyorum. Yani şurası sabit kaldığı için buna paralel bir şey çizmem lazım artık. Yani yeni magnitude şöyle bir şeye benziyor. Kompanse edilmiş magnitude. Şu da fazın yaklaşık olarak neye benzediğini çizmeye çalıştım.
Hocam iki korner arası 20 nasıl verdim bu kezde?
What do you mean?
İki korner arası iyi azalıyor.
Hı hı. Şu yani şuradaki difference'a bakarsanız o difference'ın slope'u 20 desibel per decade. Yani şu difference'ın Okay. So here we have completed our phase lead compensator design. So when can such an idea might not actually work? So if I have something like this. Suppose that this is my magnitude, okay? This is the uncompensated system gain plot or magnitude plot, okay? And suppose that you have here minus 180 and minus 360 given like this, okay? Suppose that you have a type 2 system, and suppose that you have something like this, okay? In this case, I'm going to actually read the phase margin of the uncompensated system. Let us say that this point is minus 200 and let me say here 90. Okay. What is the phase margin of the uncompensated system? This is minus 180 degrees. Phase margin is going to be, you're just going to add 180 to this number. Okay? The phase margin of the system is what? Minus 110. So here I can say that the uncompensated system is unstable. Okay? And suppose that my requirement is phase margin is larger than or equal to 45 again. Okay? How much phase should I add using phi max?
160.
Yes, approximately 160 degrees. Can I add by using this compensator? Can I add it somehow? Can this phi max be larger than 90 degrees? No, it can never be larger than 90 degrees. Okay? So here, in this type of system, this phase heat compensated, a single phase heat compensated design might not actually work. So what should I do?
Phase back.
Yes, that is one idea. I'm going to try to explain what that is. But using only phase lead, hani 348 soruları vardır. bizim zamanımızda öyleydi yani. O elemandan sadece 2 tane var falan diyor. O elemandan sadece 3 taneyle bu devreyi kurun falan. Bizim zamanımızda öyleydi yani 348 dersinin soruları. İnanmazsınız ama bizim zamanımızda bu 348 vardı. So what should I do? Yes, I need to use 2 or 3 phase heat compensator at the same time. Okay? I concatenate them and I add this phase using more than one phase heat compensator. Okay? I can actually do that. But actually, as your friend told you that there is actually a better way. So instead of using that compensator, we're going to be using a phase lag compensator. But in general, that is not going to be working in this example. I will try to explain it. But before that, here we have a practical constraint we usually tell students. If phi max is larger than or equal to 60 degrees, in general, we try not to use a phase lead compensator. Because this phase lead compensator is implemented using some circuit components, okay? So, and you require some capacitors, inductors, etc. If the required phase margin, phi max, if it is larger than or equal to 60 degrees or something, then we start to get really strange circuit elements. For example, capacitors with very large value, which are no longer practical to implement. Okay? So in general, we try not to use a single phase lead compensator with phi max larger than or equal to 60 degrees. If we need more phase, we use multiple phase lead compensators, we concatenate them, we get that phase increase using that type of topology. Yeah.
Birkaç tane eği kullanırken hepsinin omega n'leri aynı yerde mi?
Yes, you can try to do that, and then you can. So what you can do is actually that if you put omega m's at the same locations, then things would really become easy. You have the flexibility to choose them at different points, but if you use them at the same time with same omega m's, then you're going to just multiply this phase curve by 3 and multiply this magnitude curve by 3. Okay? In that case, you would, when you have a match, plotting the body plots of the overall compensator is going to be much easier. Okay? So in general, we don't use a single lead compensator if the phi max is larger than or equal to 60 degrees. So here I will try to show you something else, and I will try to motivate the phase lag compensator. So here, let me say that this is again our magnitude curve, and this is again, so in this case, let me say that this is starting from minus 90 degrees, minus 180 degrees, and I have minus, let me say, 270 degrees. Okay? So suppose that the phase is given like this. I will draw a very sharp phase here, and let us say that we have phase given like this. Okay? It starts from minus 90 degrees, and then it changes quite sharply here, and then it settles at minus 270 degrees. Okay? So in this phase lead compensator, if you try to design a phase lead compensator for such a system, can we do it? So here is our uncompensated, so here let us say that this intersects it somewhere here. Okay? So let us say that we have initial phase margin exactly equal to 0. Okay? In this case, this crossing happens to be, let us say, at minus 180 degrees. Then if I would like to increase the phase margin to 45, then I'm going to use 45 plus some error margin, 5 degree. Okay? But what is going to happen when I add the compensator? When I add the compensator, this magnitude is going to shift. The new gain crossover frequency is going to come somewhere here. But we see that phase really decreases quite fast here in this system. So your error margin of 5 degrees will no longer be sufficient for you to be able to design your phase lead compensator. Okay? So if the phase is decreasing quite sharply around the gain crossover frequency, no matter how much error margin you add, you might not sometimes design a phase lead compensator. Okay? So now, what would happen if I had the following type of compensator? Instead of phase lead compensator, I multiply everything by minus 1. Okay? Suppose that I have something like this. Okay. Can I use this type of compensator? This is called a phase lag compensator now. Okay, and everything is multiplied by minus 1. Okay, so this is minus and this is minus. So in this case, how can this thing be useful? There is a negative gain coming from this type of compensator. Okay? There is a negative gain coming from this type of compensator. If I can actually reduce this gain crossover frequency just a little bit, if I add a negative gain here to the system, if I can bring the neo gain crossover frequency somewhere here, I have really a very large phase margin in that case. Okay? If I can reduce this, then reduce the gain around there, we're going to be fine. Okay? But when I reduce the gain using this type of gain profile, then we see that there is a phase decrease coming with the phase lag compensator. Okay? In that case, what would happen is that there will be a negative phase added to the system there, which is going to be a side effect that we would like to get rid of. Okay? So in the phase lag compensator, this type of border plot belongs to a phase lag compensator. In that case, we use this gain to achieve our increase in phase margin, but the phase becomes a side effect. Okay? How can I solve that side effect? No, here what we can do here is that this gain decrease continues until infinity in this compensator. Okay? This negative gain would continue until infinity. Okay? So instead of placing this minimum phase point somewhere around here, I can place it to the left as possible. Okay? So I can try to place this peak or dip of the phase to as much left to the left as possible here. Okay? Bunu olabildiğince sola doğru yerleştirirsem aslında şuradaki gain decrease'inden yararlanacağım ve de burada fazla decrease'i minnacık kalacak. Yani bunu alıp olabildiğince sola atarsam aslında yani şu faz decrease'i ta gidiyor şuralarda yaşanıyor olacak. Ama gain decrease'i hep buralarda hala devam ediyor olacak. Okay? So that is actually what we will be doing in phase lag compensator design. When you look at a phase lag compensator, so here the transfer function is going to remain the same. You might reverse the transfer function and still use the same thing. But instead we are going to use the same transfer function and we will change one thing only. What is that going to be? What might that be? Yes. We will just take alpha larger than 1. Okay? If alpha is larger than 1, then these corner frequencies is going to change places. Okay? When these corner frequencies change their places, I will have 1 over alpha t here, 1 over t here. Okay? So the first thing in this transfer function that is going to be active is going to be the denominator. I will first hit the corner frequency of the denominator. So the transfer function is going to be 1 or 0 dB at low frequencies. And as soon as we hit the corner frequency of the denominator, we are going to get a gain decrease with minus 20 dB per decade. And then we are going to hit the corner frequency of the numerator. So this is going to settle at a value. Okay? And then what is going to be this minimum magnitude value here? What do you think it's going to be? 20 log what? Let omega go to infinity. It is 1 over alpha. Bu aynı çıktı. Ne olacak aynı? Niye aynı? Transfer fonksiyonu aynı zaten. Sadece alfanın magnitude'u değiştiği için o negatif oldu. This formula is going to remain the same. I have the same magnitude, but this time this is smaller than 0 because 1 over alpha is smaller than 1, meaning that I have this magnitude here. Or you can say minus 20 log alpha. That is the same thing. And if I draw the phase, I see that the phase is going to be just the reverse of this thing. Okay? And then what we are going to do in our design is that I will just try to get the required phase margin by adjusting the gain crossover frequency here. I will know how much I will have to decrease the gain in order to reach the desired phase margin value. Ama bugün için yeterli sayıda konuştuğumu ve zaten beyninizin çok daha iyi durumda olabileceği bir günde anlatmayı bunu tercih ederim. Teşekkür ederim dinlediğiniz için. Muhtemelen lead'ler dahil olmayacak ama onu bir e-mail'de duyuracağız. Tamam. Şu anda lead'leri dahil etmem gerekiyor. O zamana kadar. Şu anda böyle ama e-mail